All right, well, good morning. Let's get this going. This is our final exam review. I hope everyone has a copy of it. Remember, at the end of the hour or so, put your name on it, hand it in, and this counts as an extra credit. There we go. All right. Start off here with some very simple nomenclature. This goes back to chapter 9. We have an alkyne. We remember that alkynes and alkenes, we want to give the triple bond the lowest possible number if there's nothing else in the molecule. So we want to make this guy number 1 down here. So we're going to just count through this way. We have 1, 2, 3, 4, 5 carbons. So it's a pentyne. And over here in carbon number 5, we have a bromine. So it's a 1 pentyne. You have to put the 1. And over here in carbon 5, we simply have a bromine. Chapter 7 here, naming a simple alkene. Once again, we want to give the double bond the lowest possible number. So we're going to start numbering down here, I guess. That means our double bond is going to be in carbon 1, 2, 3. In carbon 3, we also have an ethyl group. And then 4, 5, 6, we have a methyl. So it's going to be a 3-octene. We have stereochemistry, or do we? Nope, both of these groups are the same. So if they're both the same, we can't do E and Z, can we? So we simply need to name our ethyl group and our methyl. Stereochemistry does not apply. This guy goes back to chapter 4-ish, I believe. We're dealing with a cyclohexane. We have a bromine and we have a methyl. There are positions 1 and 3 in the ring. We will let the bromine be carbon 1 alphabetically. So we're going to have a 1 bromo, 3 methyl. Now this is axial equatorial, isn't it? Axial equatorial, 1, 3, they're on opposite sides of our ring plane, so they are trans to each other.
Yeah, it says no stereochemistry.
When I said no stereochemistry, I meant RNS.
Oh, okay.
A much better way to name these guys would be to simply figure out RNS for each center. But on this portion of the exam, no RNS. Any question? Very simple nomenclature. Your final exam will have similar, fairly simple nomenclature. Next, we're doing a very muted sort of synthesis question. We are taking an alkyne, and we are simply making a series of derivatives. So all we need to do is indicate the reaction conditions over each of the arrows. Okay? And our first one, we are converting the carbon that's adjacent to the ring here into a carbonyl. So we're making a ketone. Now, when you think about this, we're putting an oxygen on this carbon. This is a secondary carbon. Out here, that would be a primary carbon, ignoring the multiple bond. So this could be called the Markovnikov carbon. what we're going to do in this hydration, we need to put the oxygen on, is a Markovnikov hydration. The product we're going to form is going to be the enol. Now in 235, enols are going to be very important to you because when you have an enol or an enolate anion, you actually put negative charge on this adjacent carbon. And you can use that as a nucleophile, but that's later in life. So we need to hydrate at this position, this Markovnikov carbon, for Markovnikov hydration of an alkyne. Really all you need is acid and water in the presence of mercury 2. Our next reaction, we've actually added a carbon to our alkyne. This is it over here. We know that we can do that. We can add things to a terminal alkyne simply by making the alkyne anion and then reacting it in an SN2 reaction with something like an alkyl halide. We're adding one carbon, so our alkyl halide would be bromomethane, something like that. And in order to make the alkyne anion, we simply have to react the alkyne with sodium amide. Remember, sodium amide is sodium previously dissolved in liquid ammonia. Not the fizzing reaction. Let it finish fizzing, then you add your sodium liquid ammonia to give the alkyne anion, bromomethane in the second step to add the carbon. Just like any other SN2 reaction, this works well for primary alkyl halides. Our next reaction here, we are taking our alkyne and we are doing a partial reduction. We know that if we take an alkyne and we reduce it with hydrogen on charcoal with platinum or palladium, that's a very powerful reductant. It's going to take it all the way down to the alkane. However, we can do partial reduction. We know two ways to do that. One is the dissolving metal reduction, that is sodium actively dissolving in liquid ammonia. If we did not have a terminal alkyne, that would give us trans stereochemistry. We can also do a partial reduction with a poison catalyst. Poison catalyst, Lindlar catalyst is poisoned. You could just simply say platinum on barium sulfate. That's also a poisoned catalyst. Because we don't have stereochemistry, either one of those will work. Remember, this is a dissolving metal reduction, so the lithium liquid ammonia is dissolving in the presence of the alkyne. And our last one here, we are again hydrating our alkyne. The oxygen is going out here to the terminal carbon. Now, if this is the Markovnikov carbon, this guy must be the anti-Markovnikov carbon. We're going to make the enol once again. Enol will convert into the carbonyl compound spontaneously. And the reaction conditions for anti-Markovnikov hydration are simply hydroboration, oxidation. Enol is formed initially, spontaneously reorganizes to the carbonyl. Any questions here? All right, now we're going to do it all backwards. Here we have a set of reactions, and we simply want to do our products. Your exam may have a few more reactions than on the sample exam, just so we're sure to cover everything. Our first one, once again, we're taking an alkyne, so back to chapter 9 here, and we're doing hydration in the presence of mercury 2. That's going to give us Markovnikov addition. We're going to hydrate, and the oxygen is going to go here on the central carbon. We're going to wind up with a 3-carbon enol, which will tautomerize to a 3-carbon ketone. And we just made acetone. Two moles of methyl magnesium bromide in ether, followed by standard acid workup. We're dealing here with a carboxylate ester. Now, the thing to remember on a carboxylate ester, oops, I just noticed that I put the wrong answer on my slide. Oops. I wasn't feeling well last night at all. But the thing to remember when you're reacting a carboxylate ester is that the alcohol portion of the ester is totally lost. So that just goes down the drain. What you're going to do is add 2 moles of your Grignard reagent to the carbonyl carbon. So even though what I'm about to show you is the incorrect answer, what we would wind up with would be the original methyl group and then 2 more methyl groups from a Grignard. We will make a tertiary alcohol that will not look like this. Again, this should be a methyl group here. I apologize for that.
Is it still an O on top, or is it an OH?
No, this is gone.
Okay.
This is a mistake. Scratch it out, etc. This should be a methyl group at this position.
Okay, but it's
The whole phenoxy group here, the whole alcohol portion of the ester is lost. Only the thing attached directly to the carbonyl survives. So we have 1, 2, 3 methyl groups.
1, 2, 3.
Our last one, this goes back to chapter 8, I think. Simple hydration of an alkene. How simple can we be? We are just going to add water across. This is going to be a Markovnikov addition, so we will wind up with the secondary alcohol. Right, I apologize for the mistake in the slide. The phenyl group is not here. This should all be a methyl group. Whenever you deal with an ester, the whole alcohol portion, so this whole thing is gone. Doesn't matter what it is, it is gone. Only the thing attached directly to the carbonyl carbon survives. Let's get that off there. Wait. All right. Put it back. It's just so embarrassing when I make a mistake. I just want the slide gone. Well, really was not doing well last night. I am so sorry. There's another mistake coming up. Well, here we have a simple alcohol, and we have thionyl chloride and pentane. Now, pentane, we all remember, is a nonpolar solvent, isn't it? Now, thionyl chloride, we have two reactions we can do. One involves an SN2 as our second step, and the other one involves an SNI in the second step. The SN2 reaction, of course, with a chiral center, will lead to inversion of configuration. If you do that reaction, however, in the presence of a nonpolar solvent, we get a front side attack, and we get retention of configuration. Now, when I did this last night, I misread this. I thought this said pyridine. I don't know why, but it doesn't. It says pentane. Therefore, the correct product, we will simply replace the OH group with a chlorine. The stereochemistry will remain exactly the same. Now, if this had been in pyridine, which is a polar solvent, this is the product we would get. That is the inverted product. That's the one you would get with pentane or pyridine. With pentane, simply replace the hydroxyl group with the chlorine and leave the stereochemistry alone. I hope I got some of these right.
Are you trying to mess with our grade? First it was the third exam, now it's this.
Right. Third exam is to find all of my mistakes here. All right, our next one, we're going to take an alkyl lithium, and we're going to attack a carbonyl with it. This is simply going to be a carbonyl addition reaction, just like we had a grinder of some sort. What we're going to do is take the alkyne anion, simply add to the aldehyde. Now, since it's an aldehyde, we will get a secondary alcohol. All we're doing is making a bond from the alkyne carbon to the carbonyl carbon. This goes up and makes the OH group. Oh, I think I got it. This is the bond we just made. Hydrogen, of course, is still here. And we have our secondary alcohol. So that's one for me. And once again, back in chapter 8, we have a simple alkene. We're reacting it with mercury 2 acetate. We know that when we do that, we will get an organomercurial. In order to get rid of our mercury, we just dump in sodium borohydride, and the mercury goes down the drain. This is going to lead us to an alcohol. This gives us Markovnikov regiochemistry, but we do not have the danger of rearrangement. So Markovnikov alcohol, no rearrangement. All right. Our next reaction, we are dealing with an alkyne once again. We are reacting this with hydrogen gas, simply with platinum on charcoal. Now this again is a very powerful reductant. The reduction will actually occur in two steps. First step, we will reduce this to the cis alkene, but the cis alkene will very quickly react with another mole of hydrogen to give us the alkane. PCC and dichloromethane. PCC, we recall, is pyridinium chlorochromate. Now, chromates are oxidants. So we're going to oxidize this alcohol. If we simply used Jones reagent, which is chromic acid and sulfuric acid, we would oxidize the alcohol, that carbon, all the way down to a carboxylic acid. However, PCC, pyridinium chlorochromate, is a very mild oxidant. Total oxidation goes in two steps with, say, Jones reagent. The first is to the aldehyde, the second is to the acid. But because this is so mild, it stops at the aldehyde stage. So this is going to become a carbonyl. We have a hydrogen attached and a methyl attached. It is simply acetaldehyde. Our next one, we are doing PBr3. We know that PBr3 converts alcohol into an alkyl bromide. Now again, the first step in this is to form a phosphite ester. The phosphite ester then undergoes an SN2 reaction to give us the alkyl halide. Because it's an SN2, we would have inversion of configuration. But this is not a chiral center. So we don't need to worry about showing the chirality here of the reaction. And all we have to do is convert the OH into a bromine. Our last one, this is what I thought I was reading on the very first reaction there. This is thionyl chloride and pyridine. Now, thionyl chloride and pyridine, we form an intermediate chlorosulfide ester. The halogen anion then attacks that with an SN2 mechanism, and we wind up with inversion of configuration. So this is clearly a chiral center. You must show the OH going to chlorine, and you must show the inversion of this stereochemistry. Something like this would work fine. We've simply swapped two of our groups. Of course, that represents an inversion. Any questions? Thionyl chloride pyridine, inversion. Thionyl chloride pentane, retention. And our our first reaction here, we are dealing with an alkene that also contains an alkyne. If we were to name this thing, remember the rule is, if it makes no difference in the number sequence, the alkene gets the lowest number. So this would be carbon 1 out here. It would be a 2-ene, 4-ine. All right, we're doing sodium in liquid ammonia. This is our dissolving metal reduction. Now remember, a dissolving metal reduction will convert the triple bond into an alkene, but it will not reduce a double bond. So what we're going to do is reduce this guy, and we're going to wind up with 2 double bonds in our molecule. It'll be a diene. The stereochemistry of the dissolving metal reduction is such that this winds up with trans stereochemistry. So our total product should look like this. Trans stereochemistry on this double bond, no stereochemistry on this guy. Why is there no stereochemistry? Because there's 2 methyls. So this over here would be E stereochemistry, but nothing for here. Diiodomethane, zinc, copper, amalgam, and ether. I have a little witch's brew, but this stuff generates carbene, CH2, neutral CH2. Carbene is very, very electrophilic. It sees this nice pi system sitting here, and the carbene carbon simply sits on top of it. When it does that, it forms a cyclopropane. In order to make this look cute, you could use something like this presentation. Again, show the cyclopropane. This is the carbene carbon right here. They both, of course, must be on the same side of the ring, forcing the methyl and the hydrogen cis on the other side. All right, this next guy, we are doing an elimination, aren't we? How do we know that? Because we're doing terbutoxide and terbutanol. Whenever you see those reaction conditions, you sit there and say to yourself, by George, I'm doing an E2 elimination. Okay. What do we know about an E2 elimination? Leaving group and the hydrogen that's removed must be on opposite sides of the molecule, and they must be coplanar. We will also form the most highly substituted alkene. So that's what we're working with here. This particular presentation, this is a derivative of what's known as a Fisher projection. In a true Fisher projection, you don't show these guys coming up or back, you simply draw the X's. You're supposed to always understand, whenever you see something like this, that is telling you stereochemistry. And these guys are always coming towards you, and these guys are always going away. It's a very nice shorthand way of doing stereochemistry. Unfortunately, they moved it from chapter whatever it was, 5 or 6, up to 28. So you will never see it. But it's a standard thing. If you just see the crosses, remember that's telling you stereochemistry. All right, in order to do this, we're going to have to take this sort of Fisher projection and convert it into something we can work with. Our leaving group and the hydrogen here must be rotated so they're on opposite faces, and coplanar. This is what we're dealing with. Two methyl groups coming up, those guys, and an ethyl and a hydrogen coming up. The iodine and the methyl are both going down. Everyone see that? That's our first conversion. Now, in order to do the elimination, we're going to have to rotate this carbon, rotate around this bond, so that the hydrogen and the iodine are on opposite sides and coplanar. So we can do this rotation just like that. Let me make it go back. Hydrogen will be up, ethyl group here will be down here, and methyl over here. Now, our hydrogen and our iodine are in the same plane. Our base, our terbutoxide, is going to come and remove this hydrogen. The electrons will flow in to form the double bond, and the iodine will grab its pair of electrons and go. When we do that, we wind up with this alkene. So again, the things to remember with an E2 elimination. Leaving group, hydrogen must be on opposite sides. They must be in the same plane. And we must form the most highly substituted alkene. Any questions? All right, let's do a very simple SN2 reaction, or two. This is our classic Williamson ether synthesis. We are just taking an alkoxide and we are reacting it with an alkyl halide. Benzyl halides are very reactive. All in the world that happens is that the oxygen attacks. This is our nucleophile, that's the electrophilic carbon, and the bromine is our leaving group. We attack, bromine leaves, and we make the ether. Our next one is also an SN2 reaction. This is a very reactive CH2. Why is that? Because it is allylic, isn't it? The allylic position is adjacent to a double bond. So it's a very reactive alkyl bromide. Once again, the carboxylate anion is going to be our nucleophile. That's the electrophilic carbon. Bromines are leaving group. We simply attack, bromine leaves, and we form the carboxylate ester. Here we have N-bromo-6-cinnamide dissolved in carbon tap. If we take N-bromo-6-cinnamide and we shine a light on it, what happens is the nitrogen-bromine bond breaks. It breaks homolytically, and that forms bromine radicals. So this is going to be a radical addition. Here we have cyclopentene. Radical additions can work essentially on any alkane, any CH1, but we know that they work very reliably when we have allylic centers. An allylic carbon, once again, is adjacent to the double bond. So these guys here and here are both allylic carbons. These form very stable radicals. These are our two allylic centers. They form very stable, resonance stabilized radicals. So we take our bromine radical, add to one of these carbons, and simply make the alkyl bromide. Once again, this is an allylic bromide. And just like this guy here, this has very nice reactivity towards SN2 chemistry. Any questions? Well, our first reaction, once again, is a simple SN2, isn't it? We are dealing with hydrogen sulfide anion as our nucleophile. We remember that sulfur, because it's below oxygen on the periodic table, is a much better nucleophile, much more polarizable, much better nucleophile in SN2 reactions. All in the world that's going to happen is that the sulfur anion is going to attack the secondary carbon, and chlorine will leave. When this does, this converts chlorocyclohexane into cyclohexane thiol. Our next one, very old reaction, we're all happy and familiar with this. We know that HBr in the presence of peroxides is going to form an alkyl bromide. However, because peroxides are present, this is a radical reaction. We're going to form the most stable radical. The most stable radical here is going to be on our tertiary carbon. That means that the bromine radical adds to the secondary carbon. This gives us anti-Markovnikov alkyl bromide. Markovnikov carbon would be the tertiary, so this is the anti-Markovnikov carbon, and we simply make the alkyl bromide. Our next reaction, we've actually done this, we've talked about it a couple times. Here we have a triple bond. We are doing a reduction here with a poisoned catalyst. We know that because we're doing this on the catalytic surface, we will get cis stereochemistry. But because it's poisoned, it will stop at the alkene stage, and we'll simply make the cis alkene. Any questions here? All right. Here we have tert-butoxide as our only reactants. And again, that should tell us that we're going to do elimination reactions. And these are going to be E2 eliminations. We are starting here with a bromomethyl cyclohexane. Now, what we remember about our E2 elimination is that the leaving group and the hydrogen that is pulled off need to be in the same plane, coplanar, and on opposite faces, anti and coplanar. We also want to form the most highly substituted alkene. Here I've placed the bromine axial. The hydrogen on this carbon, our tertiary carbon, is also axial. That means that these two are in fact coplanar and they're on opposite sides. So we're all set up here to do a simple E2 elimination. Tert-butoxide will pull off the hydrogen. We'll make our double bond and bromine will leave. Now this guy, the next one, this is just like the one we did a little bit ago. You're going to have to do the same operation. So if you haven't done this now, let me hush for a second. Go ahead and convert this into a sawhorse with hydrogen and ethyl up, hydrogen and methyl up, bromine down, ethyl down. Rotate it so the leaving group and the hydrogen are on opposite faces, and then do your elimination. What you're looking for, what you're looking to decide here, are the ethyl groups going to be on the same side of the molecule? That is, will they be trans? Or will they be on, the same side would be cis, or will they be opposite sides for trans? Go ahead and do the operation if you have. Step 1, draw the sawhorse. Step 2, rotate so the hydrogen and the bromine are opposite. And step 3, do your elimination. Our sawhorse. Oh, I also said Damon. Obviously, this is 1-methyl-cyclohexene. I forgot that. All right, our sawhorse here should look like this. Ethyl and hydrogen up, hydrogen and methyl up. Step 2, we have to rotate the front carbon so the hydrogen and the bromine are in the same plane. Rotation would look like this. Once again, going backwards. Hydrogen simply goes up, methyl down, ethyl up. Now the hydrogen and the bromine are in the same plane. We can do our elimination. And we wind up with an alkene where the two ethyl groups are on opposite sides of our molecule. Now we're supposed to name this. Probably want to start off numbering up here, I imagine. So this is going to be a 1, 2, 3 alkene with a methyl group. Overall, it's going to be 1, 2, 3, 4, 5, 6, so it's a hexene. Our highest priority groups are going to be the 2 ethyls, and they are on opposite sides. So this is an E, 3-methyl, 3-hexene. Okay, our last one here, we are also doing an E2 elimination. And we look at it and we say, oh my goodness, it's gonna do this thing again and blah, 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 right? Well, you don't really have to, do you? Because we realize right away, hopefully, that we have 2 methyl groups on this top carbon here. So we don't have to worry about stereochemistry, do we? We are simply going to do the elimination, going to pull off this hydrogen, the bromine is going to leave, and we will wind up with an alkene. Again, because we have 2 methyls on one of the alkene carbons, there's no stereochemistry to worry about. And if we name this guy, we would let this be carbon 1 here. So this is going to be a 1, 2, 3, 4. It's a butene. It's a 2-methyl 2-butene. Any questions? Well, in our review yesterday, or Tuesday, we had a great time doing Williamson ether syntheses 2 ways. So let's go ahead and do one of those. Go ahead and make this ether using 2 different alkoxide, alkyl halide pairs. Now, if you haven't done this yet, go ahead and think about how you do it. Remember that because we're doing this in an SN2 reaction, we're making the bond to the oxygen. So we can split on either side of our oxygen to come up with the alkoxide, alkyl halide pairs. So let's just choose one side. If this was the bond that we made in our reaction, then the alkoxide is this half of the molecule. The halogen, our leaving group, was attached here on this side of our molecule. Therefore, the alkoxide was simply 2-propanol oxide, and the alkyl halides simply had a leaving group. We'll choose bromine at this point. Now once you've done this, all you have to do is go to the other side of the oxygen-carbon bond and do the same operation. Our leaving group was now attached to the 3 carbon unit, so a bromine at this position. And the alkoxide is simply the other whole half. So this is going to be the oxide of cyclohexanol, and this is going to be 2-bromopropane. Any questions? All right, I think that the next thing in the exam is a series of fairly simple multiple choice questions. What is true regarding an SN2 reaction? Rearrangements commonly occur. No, that never happens in an SN2, does it? Only get a rearrangement when we have a carbocation intermediate. Intermediate radical does not undergo rearrangement. Well, no, a radical would not, but an SN2 reaction does not involve a radical intermediate. No intermediate at all, just a transition state. The most stable carbocation is formed. No, in an SN2 reaction, there is no carbocation intermediate. So all of these are nonsense, and this is a none of the above. Remember, an SN2 reaction has a concerted transition state. SN1 reaction. In an SN1 reaction, what is true? Well, concurrent E1 eliminations are common. Remember, in an SN1, we're going to make a carbocation. In general, that carbocation can do 2 things. We can have substitution, or we can pull off an adjacent hydrogen and do elimination. So A looks pretty good to me. Rearrangements of the carbocation is common. Well, yeah. Anytime you make a carbocation, it can rearrange. The reaction is favored by polar protic solvents. Well, think about it. You're going to take a nice neutral alkyl halide and make ions. What's going to promote that? A polar solvent. So we want to break this covalent bond, make ions. Looks to me like all of those are correct responses. E1 elimination. Because of steric effects, the least substituted alkene is typically formed. Well, you know, that sounds official enough that it could be like white, but of course it's not. In an E1 reaction, we're going to form a carbocation, and we're just going to rearrange that, and then we're going to pull a hydrogen off of an adjacent carbon. So that's not good. Elimination occurs antiperiplanar. Well, for an E2 elimination, this is true. Antiperiplanar simply means they must be in the same plane and anti to each other. So opposite sides, whatever. This applies to an E2 elimination, not E1. Sterically hindered bases tend to favor elimination over substitution. Well, when you have something big and ugly that can't get in there to substitute, it's going to act like a base. This is the best answer. Here we have an alkyne. We're reacting it with BH3 and THF. Again, we're looking for the statement that is correct. Work up with alcohol and peroxide will yield an aldehyde. Well, we know that BH3THF is going to yield an anti-Markovnikov product, isn't it? In this case, we're going to put our oxygen here at the terminal carbon. When we dump in alkaline peroxide, we will get an aldehyde. Work up with aqueous acid yields the rearranged ketone. With lots of things wrong with that. First of all, we don't ever get rearrangements. Secondly, it's anti-Markovnikov, so there's no ketone. And third, if you took the intermediate here and dumped in aqueous acid, you actually get reduction, or addition, not to give an alcohol, but you get an alkane. So, none of those work. This is the one, in the boron intermediate, the boron onto the benzyl carbon. Nope. Remember, it goes anti-Markovnikov. So alkaline peroxide gives us the aldehyde. Reaction of an unknown compound with acidic potassium permanganate gives us a carboxylic acid and CO2. What is our unknown compound? Now, what in the world does acidic permanganate do? It splits carbon-carbon double bonds, doesn't it? It splits them. Now, what do we know about the products in this distribution? If we have a hydrogen anywhere, that's going to wind up as an oxygen on either of our sp squared carbons. If we have alkyl groups, they survive. Okay, our choices. We're dealing with a tetrasubstituted alkene. That would simply split the double bond and make two ketones with it. A disubstituted alkyne. Whenever you have an alkyne, you wind up with carboxylic acids. If we had a disubstituted alkyne, we would wind up with two carboxylic acids. A trisubstituted alkene. Well, this is going to give us a ketone on one side, and it's going to give us carboxylic acid on the other. A terminal alkene with one alkyl substituent. Terminal alkene, the CH2N, is going to wind up as CO2. The thing with one alkyl substituent will be a carboxylic acid. A disubstituted alkene, that would give us two carboxylic acids. So we're looking at this reacting with permanganate, simply splitting off everywhere that there's a hydrogen, two of them here, we get an oxygen. This hydrogen also goes to make the carboxylic acid. This is a terminal alkene. Any questions? Oh, isomers, my gosh, how simple can we get? Remember isomers? The good old days, right? We want to know which of these are isomeric. Simplest thing to do is just to add up the carbons and the hydrogen, right? We look at this guy, this is going to have 2 degrees of unsaturation, isn't it? One for the ring, one for the double bond. We have 7 carbons and 12 hydrogens. Our next one is also 2 degrees of unsaturation. We have 5, 6, 7 carbons and 12 hydrogens. All we've done between A and C is move our double bond. That certainly isn't going to change the formula, is it? Therefore, this is also C7H12. This guy has 1, 2, 3 degrees of unsaturation, so you know it must be different, even without counting. If you do count, C7H10. Therefore, these guys have different structures, different constitution, but the same formula. Constitutional isomers. Cyclohexane, conformational isomers. We know that cyclohexane rapidly undergoes a ring inversion. If we have substituents, typically one conformational isomer will be more stable than the other. The rule of thumb is that axial substituents are bad. Equatorial substituents have much less interaction with the ring hydrogens, and they're more stable. So, in general, the most stable conformation will have the greatest number of equatorial substituents. I think we just said that. Ring inversion requires complete 180-degree rotation around one carbon-carbon single bond. Well, you can't really do that without breaking the ring open, can you? Well, that's silly. Equatorial substituents are disfavored. You can stop reading right there. Because, of course, they are favored. Much less interaction with the ring hydrogens. In general, the more equatorial substituents, the more stable. All right, this is an exercise that we all grew to know and love some time ago. We have a boat cyclohexane, and we must convert this to a chair. And then we're going to talk about methyl groups being axial or equatorial. So we remember, in order to convert a boat to a chair, all you really need to do is grab one end or the other and pull it down. Now the way I tend to do it is I take a perfectly drawn cyclohexane skeleton, put in bonds for my substituents, and then fill it in. So if we started with this guy, we could overlay these two, and we would have this. Simple thing to remember as far as doing this. Just look at each of the carbons. Hydrogen is above the methyl. Hydrogen above methyl. Hydrogen above methyl. Hydrogen above methyl. And this guy is still sticking up there. In order to complete the process, we want to grab this, pull it down to this position, And when we do that, hydrogen is above, methyl is above hydrogen, methyl is above hydrogen. Now we look to see if we've done this right. We have one axial and two equatorial substituents. So this is going to win as the most stable conformation, right? So let's look at our choices. Two methyl groups are axial. Nope, that's not right. Two methyl groups are equatorial. Yeah, that sounds pretty good to me. All the methyl groups are axial. Well, that's not right. Everything is equatorial. Nope. Clearly we have two equatorial methyls. Any questions? All right, this next one is another exercise that we all really despised. We are given a Newman projection, or a molecule and a Newman skeleton, and we're asked to complete the structure on the Newman frame. We are told that carbon number 3 is the back carbon. So we have to somehow number this guy. Carbon number 3 is going to be here. If carbon number 3 is the back carbon, carbon number 4 is the front carbon. So this is going to be carbon 4, and the big ball in the back is carbon 3. Now it is really trivial. We want this in its most stable conformation, so if we have substituents, we want them anti to each other. So we look at carbon 4, we say what's attached? Well, we have two methyls, or two hydrogens, and a methyl, right? Carbon number 3, we have two hydrogens and an isopropyl. Again, to get the most stable, we want the methyl and the isopropyl on opposite sides. There's our hydrogens, and there's the isopropyl. This down here would be what we labeled as carbon 1. Once again, carbon 1, 2. The big ball is 3. Come forward to 4, and that's 5. Now, another nasty trick that I sometimes pull on a exam is to simply give you a Newman and ask you to name it. So you have to untangle it and then come up with a name. So make sure you can do it both directions. Any questions? Oh my goodness, do you remember formal charges? This is kind of a leftover from general chemistry, isn't it? Formal charges really are pretty simple, though. We're dealing with nitrogen monoxide. Nitrogen is in group 5 here, so we will have 5 valence electrons. Oxygen is in group 6. It will have 6 valence electrons. So we have a total of 11 valence electrons, an odd number. We're going to distribute these in such a way that the most electronegative element is going to get the most electrons. Oxygen is more electronegative than nitrogen. Therefore, we're going to give it an octet. So what we're looking at is a Lewis structure that looks like this. Octet on the oxygen and 7 electrons on this poor nitrogen. Now, in order to do formal charges, there was a formula that we knew once, but we really don't have to think about that, do we? Because we remember that we're going to split open all covalent bonds, and we're going to distribute the electrons to each atom. Then we're going to compare the atoms to the atom as it is in the periodic table. So let's split this guy. Oxygen now has 1, 2, 3, 4, 5, 6 electrons. Oh, I guess I started with nitrogen. So let's undo that. Nitrogen, group 5. Nitrogen has 1, 2, 3, 4, 5 electrons. That's the same thing that it has in the periodic table. Therefore, its formal charge is 0. Now we can do the oxygen. Again, oxygen has 6 electrons around it. It is group 6. This is the same as the periodic table, and it is also a 0. Now you can do the formula. The little boxes here talk about the formula. We start off with 6, we subtract 2 of the bonding electrons, those 2. We subtract all the non-bonding pairs, that's 4 more, and we wind up with a 0. I think it's simpler to just split it and then compare it to the periodic table. Any questions? More chairs. What we're supposed to do here is simply draw these things in their most stable chair conformation. When we look at our first one here, the first thing we say to ourselves is, oh my goodness, this is the terp-butyl group and it's drawn axial. We know that terp-butyl never, ever, ever is in an axial position. It essentially freezes the ring such that it's equatorial. So we're going to have to draw this with the terp-butyl group equatorial. Now, when we do this ring inversion, remember everything is axial goes equatorial. So that means our axial methyl will become equatorial. The equatorial bromine will become axial. So we start off with a chair, and I put my bonds in for my 1, 2, 4 positions. The terp-butyl group must be equatorial. The bromine must be, it's equatorial here, it must be axial. And the methyl group, well, this is the carbon with the methyl, it's axial, it must be equatorial. So putting them in, 2 equatorials and 1 axial bromine. Now in reality, this ring would not look like this, would it? Because the bromine doesn't like being axial at all, so it's going to be a distorted chair. This is going to pull down, it's going to be kind of boatish, but this is good enough for now. Once again, we have a terp-butyl group. It's at the head position on a boat. We're going to want to make it equatorial. Just looking at this, well, if this is equatorial, this methyl is clearly going to be axial. But just looking at this, I'm not sure what's going to happen yet. So let's just take and draw our structure. We know that terp-butyl will be equatorial. The methyl attached to this carbon will be forced axial. And over here, we have hydrogen above methyl. So on this carbon, hydrogen should be above methyl. And that's going to force that methyl group axial. There's our terp-butyl. Here's the axial methyl. Hydrogen above methyl. We wind up with two axial methyls. Once again, the ring really won't look like this. It will distort itself, becoming more boatish again to try to relieve the interactions of the methyls and the ring hydrogens. Any questions? Let's do a couple more. Here we have a molecule with two axial bromines. Of course, those will become equatorial. That means that the equatorial methyl is going to be forced axial. So let's draw our basic structure. Carbons 1 and 3. We're going to have bromine above methyl, so the bromine is here aequatorial, methyl is axial. Bromine above hydrogen, axial bromine, equatorial bromine. And finally here we have a boat. We're going to take this boat and make a chair. We have bromines and we have a methyl group. So here's our basic chair. Again, substituents at 1, 3, and 4. Or 1, 2, and 4. Starting out here, we have a bromine and a hydrogen. Bromine is going to be above the hydrogen, which is going to make it equatorial. That's good. Over here, hydrogen is above bromine. Hydrogen above bromine, that's going to push the bromine axial. Not quite so good. Over here, hydrogen above methyl. Hydrogen will be axial, methyl will be equatorial. We're still left with one axial bromine. That's bad, of course. And of course, this ring will also distort itself. Any questions? And the last exercise of the sample final here is the trick again that we did yesterday. And this is the symmetry of a Grignard reaction. When you make an alcohol with a Grignard, you can basically do it two ways. what you're going to do is start at the carbon bearing the hydroxyl group, and we're going to split on both sides, just like we did with the Williamson synthesis. When we do that, we're going to generate one half of the molecule, one portion, that's going to be the carbonyl, and the other portion is going to be the Grignard. On the exam, you simply draw the appropriate things in the little boxes. So let's start off by splitting here. If we split on this side of the OH group, that means that this 2-carbon chunk was our carbonyl compound, and that the rest of this came from our Grignard. The 2-carbon chunk, it's a secondary alcohol, so it was an aldehyde, and it is simply acetaldehyde. The Grignard reagent, we have a benzene ring and a CH2. That's a benzyl group. So our Grignard reagent, if this is our bond, was benzyl magnesium bromide. And in order to make benzyl magnesium bromide, you would simply take benzyl bromide and react it with magnesium NE. Any questions? All right, let's do the other half. Here we're going to split on the other side of our secondary alcohol. Now our carbonyl compound had the benzene ring, the CH2, and this carbon was an aldehyde. So looking for an aldehyde, a CH2, and a phenyl group. Yep. Now the little chunk that we added here is just a single carbon. We can add that if we had methyl magnesium bromide. And finally, in order to make methyl magnesium bromide, we want to take bromomethane and react it with magnesium NE. On your final, you can probably expect at least one and maybe two of these types of Grignard syntheses where you do symmetry. Any questions? Well, one question that you should be muddling about is, gee, we did all of this final exam and there was no stereochemistry, was there? That's because the stereochemistry portion is, once again, a take-home. Now that's good news and bad news, of course. For our final exam, they give us a 2-hour block to do it in. This would be talking for just an hour and a half. So doing stereochemistry as well would make it really close on our 2-hour limit. As I read the schedule, and I hope I'm right, Looks to me like the final exam is on Thursday, 8 o'clock in the morning, that's December 17th. And we have from 8 till 10. Nope, nope. I will also post this on Blackboard, just in case you screw up your original copy and you want to print it out. Okay. Any questions?
Sure, it's Thursday.
Thursday, okay. I'm pretty sure. I mean, I've read the schedule 2 or 3 times.
The final is Thursday, as you said.
Final exam next Thursday. Here in this room, 8 o'clock. All right, if you've got